I am somewhat concerned as to whether or not I can break the base mixture with the 1,000 pound gauge. And I'm hesitant to go to the 5,000 pound gauge for fear I might break part of the setup. So I decided to make some samples using 3/4 inch PVC pipe, and the inside diameter of this pipe is just a little bit over 1 inch in diameter. So samples made with this size would have approximately 1/2 the area of the 1.5 inch diameter samples. So at any rate, I made 4 samples here using the original mixture ratio of 1.88 to 1. It's cement to water. Now, when I use the 1.88 to 1 on the 2-inch samples, I had the water running out through the cracks and so forth. So I got a comment from a guy named Skyak, why not hold the molds together with cling wrap? And I couldn't get it to hold the molds together, but at least I got it to seal the molds better. Now I thought it was going to slump anyway, so I put these washers on top so that I'd have a little reservoir of material in case it did slump away. And of course it didn't slump, so I have these little caps here which I will cut off before doing samples. Now it turns out I forgot to coat everything with a mold release, but they came apart pretty good anyway. So I'll take another one apart for you. So there's some smaller diameter samples that maybe we can determine the strength of the base mixture so we can compare it as we add more amounts of foam. So I'm going to keep these in a sealed container with some water so that they're at 100% humidity while they cure. Well, our samples have been aging inside this container with a tray of water and some records of when they were cast. So I think we're ready to start doing some testing. Just a quick review of the samples that we made in the Part 4 video. Our basic mix has a density of 1.72 times that of water. We have some samples at 0.73, the density of water, and some samples at 0.48 times the density of water. This is one of the samples that were made with the 1.88 cement to water ratio. And this has a measured diameter of 1.01 inches, which calculates out to be 0.8 square inches in area. There's 100 psi. 200, 300, 400, 500, and there she goes. So that withstood 500 psi before it broke. Here's another sample. One hundred, 200, 300, 400, 500, 600, 700, and there she goes at 800 psi. Let's try another one. There's 100, 200, 3, 4, 5, 6, 7, and there she broke. And here's our last sample. There's 100, 2, 3, 4, 5, 6, 7, 8. So about 850. So we have a rough idea of what our base mixture can withstand, and I'll show you the results of all of our testing near the end, but I've calculated 2188 psi for the normal batch, the 1.88 cement to water ratio base mixture. So let's move on to testing the samples with air mixed in, or foam, I should say. Here's a sample, and I see there's a void in here, but we'll go ahead and test her and see what happens. There's 100 psi, and we can see the sample is just folding and crumbling. So let's try another one. Okay, this sample looks fairly good. There's 100, and it's just crumbling. And I think our less dense samples are going to be even weaker. We'll try one of those next. Here's a sample with even more foam in it. There's about 50 psi, and she's just crumbling as we go. So it should be pretty obvious that adding the foam to the cement water mix does make it much weaker. Although the foam Crete would have insulating properties and fire resistant properties. So let's at least look at those before we wrap it up. Okay, here's one of our more dense samples of the two Aircrete samples. And we see that floats pretty nicely in water. This one is even less dense. And we can see it floats even higher in the water. And here's a chunk of the base mix, and of course that sinks right to the bottom. So let's see how the Aircrete holds up to a flame compared to the base mix. Let's see how our base mix reacts to a flame. I've drilled a small hole in the backside of this cylinder about halfway up. It's about a ½ inch deep, and inserted a thermocouple. And you can see the reading on the top scale on the meter. It's labeled T1. Right now it's 78.7 degrees, and we'll turn on the flame and see what happens. If you read the book for Fahrenheit 451, you know that the backside of the cylinder is now hot enough to ignite paper, and it's still rising. Okay, here's the more dense of the two Aircrete samples. Okay, it seems to have leveled off around there. Okay, here's the less dense foam. Those aluminum blocks are getting warm now, so you can see the temperature rising. Okay, it looks like we've just about leveled off there. Some have asked, does Aircrete absorb water? So what I've done is put a sample of the base mix and the two different foam densities in this jar of water, and I have another piece of the base mix to hold everything down. And I weighed all the samples before putting them in the water. So we'll take them out and dry them off and weigh them and get an idea of how much water was absorbed, if any. Well, the samples of the Aircrete are just barely floating, so I think it's obvious they've absorbed some water. So we'll dry them off and weigh them. Here's the summary of the results from the water absorption test. And these were the weights of the samples before I put them in the jar. They were soaking in the jar for 7 days. And this is their weights after they were just dried off with a paper towel. Then after 2 hours of drying, we can see we're losing weight rapidly. And 8 hours, and then a full day of drying, we're practically back to the original weights. So the Aircrete does absorb water. and it also gives it up fairly quickly. Now here's the results of the flame test. The base mix got up to 500 degrees and was still rising when I terminated that sample. And here's the final temperature with the other two densities. Okay, here's a summary of our strength testing of the samples. Using this equation, this coefficient here has to do with the geometry of our hydraulic ram. So this is gauge PSI, but this is PSI rating of the sample. So for our base mix, with the 1.88 to 1 cement to water ratio, those samples had a diameter of a little over 1 inch, which came out to be an area of 0.8 square inches. And I threw away the 500 PSI since it was kind of an anomaly compared to the other three readings. So we had an average of 800 PSI, so that comes out to approximately 2190 PSI for the base mix. Now our higher density of the Aircrete samples is a larger diameter, so the area was 1.89 square inches. And there we had an average reading at failure of 100 PSI. So the PSI rating of the sample is about 116 PSI. Now, although that seems to be a very low number, if we had 1 square foot of that material, it would be able to support 16,000 pounds, or approximately 8 tons. The less dense sample ended up with a rating of only 58 PSI, but again, a square foot of that would be able to support around 4 tons. So let's plot these on a curve and see what we make out of it. Okay, here is a rough plot of the 3 points that we have so far. And here's our base mix. This is the compressive strength in PSI and the density of the sample compared to the density of water at 1.0. Now, these data points are probably not very accurate. We need bigger diameter samples so we can get higher gauge readings. Usually gauges aren't very accurate at the low end of the range. So we don't really know what the curve looks like here. Maybe something like that. So we really need to make some samples to get a better idea of the shape of that curve and get these points more accurate. So I'm going to have to make some larger molds for the low end here, and I think we're okay in the mid-range with the mold situation. But the real problem is everything has to cure for 4 weeks for it to reach a high percentage of its final strength. So sometimes science can be fun and sometimes it's slow and tedious.